Hello, hello. So this isn't my official office hours. Rather, someone had a random question from Facebook, and I decided to answer that question. Um,
Hello.
I figured I would just go live because it's easier than setting up a video. Indeed, it is late, later than my usual office hours. But again, this isn't real office hours. So technically, office hours aren't happening at all today. Okay, so here's a question. Um, they asked this discussion about collapsing objects in a category. Why wouldn't this make compositions work? Blah, blah, blah. So let's start 12 a.m. in Denmark. Well, then you should definitely go to bed. Get a good night's sleep. So we start with this first comment. Sort of the things are in the way, but or let's jump to the second comment. So why not collapse the objects then? They ask about collapsing objects in a category. I mean, you could absolutely do that. So, for example, let me just make a new document here. You could definitely collapse objects in a category. So, the skeleton of a category is basically, or a skeleton of a category is a choice of a full and faithful, essentially surjective embedding. So a classic example is like you could take the category whose objects are the vector spaces R1 for all finite n, and whose morphisms are morphisms from Rm to Rn are just n by m matrices, n by n. I need to, yeah, m by n, I think. I don't remember. Whatever. And then composition is defined just by matrix multiplication. Right? So this is a skeleton for the category of finite dimensional real vector spaces. Right? So basically everything in the larger category of vector spaces is isomorphic to one of these objects, but strictly speaking, this skeleton category we've defined here is way less objects, right? It's got a countable number of objects. Meanwhile, the category of vector spaces is like too big to even be a set. So you can absolutely do that. But the thing is, like, doing this is kind of a nasty nightmare, especially like if you want to go. It's like once you know that every vector space, every finite dimensional vector space is like entirely determined by its dimension, you can sort of make this guess for what the skeleton of this category should be. And you can go and prove it is a skeleton. But then, like, the result that every category has a skeleton is, like, highly non-constructive and involves, like, the axiom of choice, and it's just kind of a nightmare. You're, like, choosing, like, in this case, we happen to have, for vector spaces, there happens to be a nice way to choose representatives for everything. But in general, it's like, yeah, how do you, like, you have to make some random choice of representatives and some random choice of representatives for all your maps. And, like, how do you define composition? And it's, like, not a good thing. Yeah, it's just kind of a nightmare. So, but in short, you could do it. You could collapse objects. Now, there's this comment, surely this is a distinct category rather than letting A and B be the same object. Okay, so they're imagining that you start with some category with two objects, A and B. Of course, these have to have identity morphisms on them, and I guess they're supposing that there's just one morphism from A to B, so then it's not an isomorphism. Okay. Now, I should also mention, because, they go on to talk about trying to localize things in another way. You can't just, like sort of what they're doing in this thing here. It kind of works out in this example, but you can't just do this super naive way of localizing categories. Maybe as they ask, I will come up with an example at the end. But so let me jump ahead to that for a moment. Because the point is, what is a category? Right? A category is really a triple. It's a class of objects. It is a family of sets, one set for each ordered pair of objects. And it is a composition function that tells you how to take in two functions, right? It's really, I should say it's a bunch of composition functions, like x, y, y, z, which tells you how to map from one Hom set to a Cartesian product of certain Hom sets to another Cartesian product of Hom sets, right? So if you're going to define a category for me, you need to tell me what all of these things do. And so, for example, in this in the comments, you can see here, well, you could say, oh, I want to invert this map F. You can do that. You could say that there's a formal inverse, but now to give me a category, you need to also finish telling me how that F inverse composes with all the other maps. Now, in this case, it's very easy to do just sort of by hand. You could say, okay, and especially here because everything's finite, so we could just draw in a new arrow and define a new category F inverse. And of course, we define F and F inverse to be inverses of each other. But then you also still need to tell me, again, these conditions are basically forced, but you need to tell me what the compositions of F inverse is with all the other arrows. Again, in this case, it's very fine to do it, totally fine to do it this naively. The problem is, what if we're in a larger category that has way more arrows, right? So you can't just write down one arrow and say, oh, I'm just going to add in this new arrow F inverse. Because now you also need to tell me what is F inverse pre-composed and post-composed with every possible other arrow that makes sense to compose it with. And then once you make those definitions, you then also need to convince me that this is compatible, right? That this is like associative for every possible choice of morphisms. And so in this case, which by the way, that's another thing we haven't done yet in this naive case, which again, we could actually do once we've defined all our compositions, we can check, and it definitely holds in this case, but there's actually a lot of work to do to make this precise and rigorous. So, yeah, there's just a lot going on. This math is category theory. This is, yeah, squarely in the realm of category theory. So how do we do this more generally? This is where the concept of localization comes in. So I'm not going to review how to do it. Actually, by the way, I have a video on my channel where I talk about how one constructs the derived category using localization. So actually, I've already talked about this in an old video from like 3 years ago. I could probably make a better one at this point. But I'll have you look it up. The point is, localization is like, this is how you make a formal, rigorous construction of inverting some collection of arrows. However, you cannot just invert an arbitrary collection of arrows. The whole point, it's thematically similar to if you know the process of taking a ring and localizing that ring, right? To take the localization of a ring, like how you localize the integers to get the rational numbers, I mean, we need S to satisfy certain properties to ensure that the thing that you get out at the end of the day is actually a ring with a well-defined multiplication, and so on, etc., right? And so the process of localization is just a way that we've figured out that allows you, if you have a certain collection of morphisms in your category, subject to some certain condition, as long as they tick these boxes, then we know that we can produce in a systematic way a well-defined category that basically inverts those arrows. And again, the issue comes into this headache here. Like I said, imagine you're in an arbitrary category, right? So you don't know, you're in the case with this nice finite picture here that everything's easy to check, and you try to just invert some arrow. Well, as soon as you try to invert some formal inverse, again, just for one arrow, you need to go through and you need to define for me all possible compositions, and then you need to check that all of those things satisfy associativity. And that would just be for one arrow. And now, I mean, if you want to do this for more than one arrow in a category, like you can quickly imagine this, like at a combinatorial level, this explodes into an unprovable nightmare. Let alone, if infinitely many arrows or something. So you really want to have a nice process. So I would like go to localization. That's what you want. Okay. Now there's also this question of, are these categories, surely these categories are distinct, this person says. Now we have surely we have a distinct category rather than letting A and B be the same object. Well, what do you mean by distinct? What is your tolerance for distinct? Because, so we could imagine, so again, letting A equals B doesn't really make sense, right? A and B are two different things. You can't let them be equal, but you could imagine a category that just has one object, A, and say maybe this one arrow. Now, what is your notion of distinct categories? Well, we could say that two categories are the same if and only if they contain all the same objects, and for every set of morphisms, their morphism sets are equal, and for every possible input, the compositions agree. Okay, this is horribly restrictive and not a very useful notion, right? I mean, think about groups, right? Generally, we can be a little bit looser. We say, oh, we want an isomorphism of groups, right? So the next notion, possible notion for sameness of a category is an isomorphism of category, where you have two functors which compose to the respective identity functors on the nose, right? And so, for example, well, our objects may be a class, not a set, but still this could be bijection. And so you could take this notion of isomorphism of categories as your notion of sameness. And so certainly this category would not be isomorphic to this category because they've got different numbers of objects. So now it doesn't have to have literally the same objects. The labelings don't matter, which is probably reasonable. But this notion of sameness for categories would not allow for these two categories. So in that sense, they would be distinct. However, for example, like in this first thing I was talking about with skeletons of categories, this is, there's some sense in which the skeleton really is sufficient to represent all finite dimensional vector spaces, right? It's like anything you could possibly do with a finite dimensional vector space is basically captured by this skeleton category. Although according to our notion of isomorphism, they definitely would not be, or they would definitely be distinct categories. And so in the modern perspective, really the notion of equivalence that seems to allow the right combination of fluidity and rigidity is what's called equivalence of categories, where instead of demanding that the compositions of functors be bang on equal, we simply say they're isomorphic as functors. So there's natural isomorphisms between them. If you were to go to this level, then I have to think, are these categories equivalent? I'm a little concerned that maybe no, actually, because F gives you an extra morphism here. Like, what would be the equivalence? No, maybe they are equivalent. No, what am I saying? Would they be equivalent in this case? Well, I guess I can solve this easily, right? We send FA FA to A, and then, I don't know, maybe call it A prime for this A here. And then we send G A to A prime, G B to B prime. And I guess we need to send GF somewhere. So we would have to send it to the identity. Yeah, we would have no other choice. Yeah, I think this works. We got to check that this respects composition and everything, but yeah, I think this works. So in this case, they would be equivalent categories. Fact check me on this, though. It was a good exercise. Go do that. Okay. So moving on. Right, so then this last sentence here is really confusing me. Perhaps F won't be an isomorphism. F in where, though? In the original category? No, not necessarily. But if you created an F inverse, then you did make it an isomorphism. So I'm not so sure what that means there. Is there a reason for adding morphisms to make two objects isomorphic rather than considering two objects as equal? Well, again, I guess I already addressed that earlier with the choice of skeleton and stuff. You could, equals even, yeah. So you could first invert by the morphisms, giving you isomorphisms, then you could take a skeleton. But yeah, again, this is a nightmare to do for the reasons already listed. And as an analogy, I mean, think about picking a basis in a vector space. Very useful thing to do if you need explicit computations. Great tool. But sometimes it's better if you prove things by not picking a basis, right? If you pick a basis and perform some construction, then you need to argue that your construction did not depend on the choice of basis. And that gets very annoying having to do that after a while. So, you save yourself a bit of time if you don't have to make these choices. So yeah, as the commenter says below, a note on morphisms. If we decide to merge objects, well, what do you mean by merge objects? What do you mean by again, I have the rough intuitive notion of what you mean, right? I know the idea, but how do you make merge objects a formal, rigorous procedure, right? So to the extent of where, again, if you want to define a category for me, I need you to literally write down a set of objects, rigorously define the hom sets, rigorously define the compositions for me, right? And the process of localization, for example, can help you do this. So, by the way, and this person was asking this based on a question they posted on Math Stack Exchange, where they're talking about the there's the homotopy category, or the naive homotopy category, and then like the real homotopy category. So, basically, what one does is the real homotopy category is obtained using localization and localizing at these weak homotopy equivalences. But you have, like, that is a very precise, rigorous procedure. You should go read up on it. The naive homotopy category can be defined more naively, but okay, you still need to take some care, right? So you define your objects to be topological spaces. You define your morphisms to be homotopy classes of continuous maps. And then you define your composition. You say, well, I'm going to define composition of two maps which make sense to compose to be the homotopy class of the composition. Okay, but now there's work to do. You need to prove that this is a category. You need to prove that there's identities. You need to prove that the composition is dissociative, and so on, etc. So there's work to do. This is a basic exercise. It turns out to be a basic exercise in like a first algebraic topology course. Just proving, that the composition respects homotopy. Right, maps compose up to homotopy, but like, there's a non-trivial amount of work to make it not nonsense. Yeah. We would have let the collapsed object have all the original morphisms. Yeah, so then that's already a property. All the original morphisms. So what do you mean by all the original morphisms? If you're collapsing two objects, right, are like if somehow A and B are collapsed, whatever this vague notion means, again, what's the precise set theory level definition of collapsing two objects? What do you mean by that? I mean, you could form like the isomorphism class. For example, you could define, this would give you an equivalence relation, right? You could define like the isomorphism class to say be the set of all objects D such that D is isomorphic to A in the original category, right? That would be one choice of doing things, but like, we've got to be rigorous here. And then what do you mean by the same morphism? Because say we did do that. Well, do you mean that it's just you just pick one of the representatives and you just let hom of the like, I don't know, A tilde for the like collapsed version be this? Or are you taking it to be like the union of, as you go over all arrows, like, are you tossing in all hom B into X and all hom A into X? And then my question would be, well, if you tried to do this, like, how do you know you get a well-defined category out of this? Again, you need to go back. You need to check, like, okay, what is my composition? How do I know it's associative? Blah, blah, blah. How does this fit into the axioms of a category? Yeah. Yeah, so this person says, yeah, the collapsing is not well defined. Can I define equivalence of objects? Oh, message retracted. I don't know what the point is of retracting message. Well, I get it. I mean, maybe you say something, you realize it's silly, and then you're like, I don't want it to be on the internet forever. But, it's in chat. If people pause the video, it'll be there forever. You gotta, hey, I make mistakes all day long in this channel. You gotta rip the Band-Aid off of being afraid of mistakes to get more gooder at math. Okay, so why composition does not work? Yeah. Well, again, I mean, no one here's defined composition, right? So like it's on the onus of the reader to even define what composition means, right? So can you enlighten me why composition does not work? If I want to collapse all one-dimensional real vector spaces, again, what do you mean by collapse? I can't. Yeah. My proposal would involve essentially 3 steps. 1, collapse all one-dimensional vector spaces into a single object. I don't know what that means, but let's suppose that they mean this. This would be a formal way of doing it. So we could form a new category. So let V be the set of all U such that the dimension of U is 1. Say we're working with like real vector spaces. Okay. And we form a new category, I guess, a new category C, whose objects are what? Well, the objects are all vector spaces, all real finite dimensional vector spaces with the dimensions at least 2, and then we take the union with a set. I mean, you're right. Big quotation marks here. I mean, okay, it's not a set. Well, I believe in growth and decay universes now, so I've chosen one, and this is just it's a set with respect to my infinite hierarchy of sets, of large cardinal sets. And then we also toss in this set V. Okay, great. So we'll suppose that that's what they mean to be formal. So that's step 1. Representing them all. 2, declare hom V as a disjoint union. Okay, but now this is wild, and this is, I mean, like, now we're definitely, so we could try and do this. We'll still need to prove that the end result is a category, but so first off, actually, so one small technical set theoretic issue. Lots of times people start with locally small categories, and that's sort of the main tolerance, where you allow your collection of objects to be so big that it's not a set, but you still want your homs to still be a set. And if you did it this way, then our new category, it would still, our object class is huge. The problem is, I mean, maybe it's not a problem, but now we're getting into weirder territory. Now the category is no longer locally small, because now we're ranging over all vector spaces U and V. UV in object of vec R Ph.D. And now this is huge. I mean, this is too big to be a set. Not necessarily a problem. People consider, categories of this size all the time, but things are definitely getting weird. And now, I mean, here we already see that there's a bit of a problem, right? Because again, you could work with this. I mean, supposing that the next steps we do end up defining a category, we could go on and work with this. But now we're no longer faithfully representing the original category we had, right? Because we know, for example, that like first off, the category of vector spaces, all the hom sets themselves have a vector space structure, right? And actually, this even goes with our skeleton construction, right? M by N matrices have a vector space structure in a way that's compatible with the category structure of like composing morphisms. And so if we did this, now this thing on the right does not have any obvious vector space structure at all. And moreover, I mean, the one-dimensional vector spaces, like this is isomorphic to the real numbers itself, right? It's itself this one-dimensional vector space, has this nice structure. But now if we created this monstrosity on the right representing the one-dimensional vector spaces, then it's just it's just this massive beast. And it's like, well, now we've lost a lot of the things that we like to do in the category of vector spaces and the whole theory of linear transformations. But we can do it as a disjoint union. And then finally collapse each identity to one unique formal identity morphism. Okay, so I think what they're saying then, I think they're saying take an equivalence relation. We're actually going to define our Hom set to be this equivalence relation, where rather we just say, I guess every morphism is a singleton, except for the identity morphisms. Those all become like one class, and now we say that that's our identity in here. Okay, I guess we could do this. Right? And if the issue is that for two morphisms, we don't know whether their composition is in there, we could just formally adjoin those compositions. Well, then that's getting even worse, right? It's like, yeah. So, I mean, yeah, the problem is, again, now we're getting back to the issues we had before. So in order to finish defining this category, we need to define what all of our compositions are, right? So I guess we could always define we could just define the composition of this identity element in such a way that it just returns what it's supposed to, given the axioms of a category. That, I think, is fine. Yeah. And then I guess we could also define, like, well, so now let's say we had a Hom in here, which really, I mean, this is an equivalence class, but let's say it's the case of an equivalence class of a single element. Okay. So that's Hom V to V. And we want to compose this with something from, say, Hom V to some Hom U. And we want to get out something in Hom V to Hom U. So, well, actually, hang on. So we also, now we haven't defined what these sets are. So our definition's not even done, because now we have Hom V U. Yeah, so what's the definition of this in our new category? Undefined. I'm guessing, here's what I'm guessing is that this person would say is that, we just take the disjoint union of all the Homs in the category of finite dimensional vector spaces as we range over all one-dimensional spaces. Okay. And how could we define composition then? Yeah, now how do we even define composition, right? Because if you take F is going to just be it's going to be some map between two I'll call them X and Y, is just some map between two arbitrary one-dimensional vector spaces. And now a map in here, if we did it that way, we don't have to do it that way, but a map in there is now going to be some morphism between W and U for some random one-dimensional vector space W. So then the question is, like, Y and W don't need to compare with each other. So how could we possibly compose these two morphisms? You would have to make some choice of mapping from Y to W to get a composition. So, yeah. If C is not locally small, the composition is not a function. Right. Well, it's not a functor. I mean, you can have like functions between classes. I guess the main problem is that you're just going into the theory of classes of sets. So, well, I didn't intentionally use the disjoint union. I mean, this is I use disjoint union all the time in the real world, but this was an explanation to show why this is a bad idea. Yeah, so we run into all of these problems. And, okay, you could try pushing ahead and making all of this work. Oh, sorry, to answer the question, yeah, let me just say is one thing. So then we're popping out into classes, Mr. L, for your question. The better thing to do is just, this is exactly why everyone should just accept the existence of a Grothendieck universe. Just some, like, countable hierarchy of ever-increasing inaccessible cardinals. And let's all just happily go beyond ZFC. I have a video where I talk about this as well from, like, a couple months back. Just accept it. It'll make your life in category theory easier. Then everything's a function. It's just some sets, and everything's a set too. Well, not everything, but like you can always just call your collections of objects sets. But yeah, getting back to this. So, I'm sure, maybe the person who I made this for, you might be watching this. You might say, oh, well, I could come up with some sort of hacky way to fix this. Sure, you could try. But I'm hoping that what I've done in this way too long rambly video is convinced you that this is not a good approach. This is not a good way to do things. Lots of people have thought about this very seriously and very carefully. And really, localization of categories is the way to go for what you want to do here. And so I highly recommend going and reading up on that. And, well, some people would argue there's better ways to construct derived categories these days. But anyways, once you have localization, it does give you ways to build, to understand how the derived category is formalized. It gives you ways to understand how the homotopy category is formalized. It's just a useful tool. And keep in mind the construction of localization of a ring, because somehow it's like thematically it's really there. It's the same thing. So yeah, you probably should be content to gloss over these things, Christian. I would maybe be happier if I wasn't compelled to look at these details, but I'm not content. I really need to know the bones of things. And I would probably have proved more things that matter by now if I wasn't. But I digress. Anyways, that's all. That's this random question rant. See y'all later. Go prove some things.